Good evening, everyone, and welcome to tonight's talk. And I'm just here on behalf of Moog, and we're proud to be able to sponsor tonight's event. As Chris said, I'm the Senior Manager for Military Engineering at Moog Wolverhampton. My team design, develop, test and put into production primary flight control actuation for military aircraft, but also rotorcraft, so I have a particular interest in tonight's talk. Thank you. I'm pleased to introduce David King, our speaker this evening. I've got a brief biography which I'll read out. Hopefully it's all accurate. David served as Chief Engineer for Vertical Aerospace since February 2023. Prior to this, he spent 30 years in senior roles at Leonardo, Bell and Boeing. David's last role at Leonardo was Chief Engineer on the AW609 aircraft, something that we're very close to in Wolverhampton, having produced the primary flight controls for that particular aircraft, which is also set to be the first new category of aircraft to be certified in over 50 years, another pioneering step forward in David's career. David was also Chief Engineer for Bell and launched his commercial helicopter design and certification project, the Bell 525 aircraft, which is another aircraft that we produced the primary flight controls for. It's the first fly-by-wire civil helicopter which is going through certification as well. A whole load of innovations there. Both two programs there that Moog are heavily invested in. David holds a Bachelor of Science in Mechanical Engineering from Lehigh University and a Master of Science from Aeronautics and Astronautics from MIT. So at this point I'll hand over to David for his talk. Thank you.
Well, thank you, Mike, and good evening, Royal Aeronautical Society, Wolverhampton, Birmingham, and Cosford branch. So it's a long but distinguished name. It's a privilege to be here with you tonight to talk about innovations in aircraft design, because this part of the world is where a lot of aircraft design innovations happened. Think back to the Wright Flyer 122 years ago, and you look at that 122 years of aviation, and I'll show you a curve that you've got the first 60 years, there are all kinds of different types of aircraft being introduced and flown. A lot of that happened right here in this part of the world. But then the last 60 years of that curve, not so much. And so what we want to talk about is, okay, why? What are those barriers to entry? So I wanted to share with you, my experience on what I've seen in terms of these barriers to entry and what we can do to get over that. I was at a conference with the aerospace and defense investors in New York City right at the beginning of this year. And one of the keynote speakers put a slide up there, and it's just one line. He said, "We have an innovation problem in commercial aviation." And you think about it, we do, right? We do. That there are capabilities out there that aren't making it from the engineer's mind into service because of some barriers. So that's what we're going to talk about. I'll share my experience, and I have had some really good experiences working with the engineers in this part of the world from my days in particular at Bell. Carlos Fenny, who's a good friend of mine, he and I spent a lot of time in the Bell VTOL lab with some Moog actuators, injecting all kinds of failure conditions into it to see if we could break it. We couldn't. So some great engineering comes from here. From my perspective, to give you a little background, so my aeronautical engineering degree is from the 1980s, and since then I've spent my life's work developing new types of vertical lift aircraft. And that I want to kind of look at it from that perspective. And when I started studying aeronautical engineering, there was a lot going on right in the 1980s, in particular on the defense side. And I thought about that 2 weeks ago. I met with a group of students and faculty from Embry-Riddle University, all aeronautical engineers, and the icebreaker in the room was, hey, let's go around and say, what inspired you to become an aeronautical engineer? And everybody had a story, and every story was a little bit different and unique. Now I assume if you did the same thing to a bunch of finance majors, their answer would probably all be the same. They're going to make money. But in the aeronautical world, everybody had an interesting story. So my story is I grew up in a little neighborhood that was right on short final for runway 24 at KABE Airport in eastern Pennsylvania. So I would spend my time as a kid in the backyard on the swing set, and I'd see the airplanes coming in, gear down, flaps set, flaring to the touchdown. And it was just that romance of flight. So when I saw this quote from Juan de la Cuerva, vertical lift pioneer from the 1930s, when somebody asked him about what got him inspired, he said it was the combination of the romance of flight and the beauty of mathematics. You think about that, that's what engineering new aircraft requires, right? It requires that inspiration of what flight you want to accomplish, but then it requires that mathematical rigor. The ability to be able to take the physical world and predict the cause and effect in mathematics. And I also, growing up, both of my parents happened to be professors of mathematics, so I had a lot of that at a young age. So let me introduce now our company, Vertical Aerospace. So Vertical Aerospace is based in Bristol. It was founded in 2016 by Stephen Fitzpatrick, who is also the founder of Bobo Energy Company. So Stephen was referred to by the Wall Street Journal as a serial entrepreneur. Now, you often don't see entrepreneurs and aircraft OEMs linked up that often. So here's a story. So 2016, at the time, Stephen owned a Formula One team. That team had a race at the Grand Prix in Sao Paulo, Brazil. Stephen had a meeting in the center of the city just before the race, and he gave himself about an hour and 15 minutes. He thought that was plenty of buffer to get from Center City to the race, which was 9 miles away. Took him 2 hours and 15 minutes, and he missed the start of the race. The meeting that he had in the Center City was to talk about the potential to introduce electric motors into Formula One cars. So Stephen had just been briefed by the engineers, and Stephen wasn't an engineer. He was not a formally trained engineer. He was taught, okay, here's what type of power density we can get out of these electric motors. And he was running the numbers. Okay, 0 to 60 in 2.2 seconds. Okay, what type of thrust can you generate? And while he was in that taxi stuck in traffic, knowing he was going to be late for his race, he wanted to just reach up and press a button and lift his taxi up vertically, hover, fly over the congestion, and get to the race on time. So that was the genesis. He saw a problem and he saw a solution on the same day. The problem being urban areas right now are so congested that mobility keeps getting worse and worse and worse. The solution being the advancement of electric propulsion. So he founded a company, and his company is built as a conventional aircraft OEM, with the exception of it's also a battery company. So at Vertical Aerospace in Bristol, we have an energy center where we develop, design, test battery systems, but we're predominantly a classic aircraft OEM, where we take the collective wisdom of a broad and expert supply chain and the collective wisdom of an experienced set of operators that we deliver the aircraft to, and use that collective wisdom to develop an innovative solution. If you've seen some interviews with Stephen on the news, there's one line that he likes to say, and he said, if I knew it was so hard to innovate in the aerospace sector, I never would have gotten into this. And so it kind of reminds me of the old, you probably heard it, the advice that came from Howard Hughes, where he said, hey, how do you become a millionaire? He said, well, you start as a billionaire and then you get into aerospace. So now, let's rewind the clock to 10 years later. 10 years later, we are at a point now with the company in Bristol. We're 450 employees strong, and we've looked at the 3 streams that we've been busy working on for 10 years. The one is mature the technology. Take what the automotive industry had already matured, turn that into an airplane technology that meets the market demand and is certifiable. Number 2, let's make sure there's a clear path to certification. This is a new category of an aircraft. What are all the safety standards? Safety is paramount. And then number 3, let's produce a design. Let's take that learning from the maturation, the market fit, the certification, and put together a design. So let me show you where we are on that.
As our skylines rise ever higher, our streets stand stubbornly still. Congestion grows. Opportunity trapped on the ground. Until now. Introducing Velo from Vertical. Engineered for safety, space, and serenity. Clean, quiet, and fast. Crossing cities in minutes, not hours. Velo is not a concept, it's here. This is the new urban mobility. Velo is a new era of possibility for everyone. All you have to do is look up.
All right, so why eVTOL and why now? Because it's about time. Let's look at the history of innovations in new aircraft design. Go back to the first 60 years, which is the Wright Flyer took to the air in the first powered flight. The first 60 years were a really steep curve of innovative aircraft concepts being engineered, being developed, being flown, and being brought into service. What drove that? What was the impetus that drove that first 60 years? There were some grand challenges, of course. So there were two major global conflicts, World War I, World War II. There was this broad green field of innovation space. Because powered flight was so new, there was a lot of innovations and a lot of inventions that could be built on top of that. There was also the industrial growth in the Western world. So there was an impetus from communities, from governments, from nations to grow their economies and use airlift to be able to accomplish that. Then you look at the next 20 years after that, and you see the innovation curve continue steep. But at the same time, you'll see the fuel cost curve built into that. And then the fuel cost is a driver that we'll show you in here. But you see a number of different companies and a number of different models. So the one curve on here is showing, the green curve is the number of companies that were founded to produce aircraft in a different design. So the number of companies skyrocketed in the first 60 years, started to come down a little bit more the next 20 years, but still there was a good, healthy competition. If you look at those years in the consolidation era, you'll notice that there's a call out here for vertical takeoff and landing aircraft that were operated under an airline called New York Airways. So New York Airways operated vertical takeoff and landing from Midtown Manhattan to JFK Airport, where then the passengers could board a 747 and fly across the ocean to London, and then get from London to here. So that airline was an innovation that was around in this period of rapid growth. Then the 20 years after that, the innovation curve flattens out, consolidation starts to accelerate in terms of shrinking the number of companies in the aircraft industry. Then look at the 20 years after that, and you'll see a flattening more of the curve. Not a whole lot of new aircraft introduced. You'll see there was a little blip associated with the supersonic in the Concorde, England's own Concorde that came about and then flattened out. You'll see that the red curve, that there was a number of iterations on the fuel cost trends. And then you look at the last 15 years, 20 years, and you'll see a continual flattening of innovations from an aircraft design concept. Now, if you think about this, this is the aircraft design, the new clean sheet designs. There are a number of innovations that are going on at the system level and at the component level, and those are driven largely at improving the efficiency of the aircraft, its fuel efficiency most specifically, and then also the manufacturing costs and the efficiency of operations. But what you don't see is the new capabilities being introduced. So if you think about technology in general, and you think about what you do in a day, what you do in a week, you think about how technology helps you live your life by making it easier and faster to do your day-to-day tasks. One day-to-day task hasn't gotten any faster. In fact, it's gotten slower over these past 60 years, and that's mobility. If you look back at that point that showed New York Airways in the late 1960s, that would allow somebody to check in for a flight from New York to London 45 minutes before the flight departs, but they would check in the office building in Midtown Manhattan. So they would get in the lift and go up instead of down. They would go up and check in, fly 10 minutes, land behind security, get on the airplane, their bag gets loaded, they get on the airplane. Think about how much time that would save you. I don't know if you've commuted from Midtown Manhattan to JFK, but it could take you an hour and a half. It'll cost you $160 with a tip in an Uber XL. And then to get to JFK Airport, you're supposed to get there 3 hours ahead of time. And now with the Department of Homeland Security not funded, you got to give yourself maybe another hour to get through. So that's 4 hours plus an hour and a half, that's 5.5. So that's 5.5 hours to get there, whereas it's 40 minutes back in the 1960s. Right? I was born in the 1960s. That tells you how long ago that was. However, you look at the innovations that have been going on at the system level, and there's the fuel efficiency driver, but then there's also the safety driver. So that is one thing that is a testament to the ingenuity at the tier 1 companies and the ingenuity of the small companies that feed the big tier 1s. Now the big tier 1s, I think Moog is a prime example, have bought a lot of those smaller companies that have come up with some really clever, innovative. And what that's allowed the aircraft design industry to show is over the past about 30 years, you see that the safety record, the accident rate of scheduled airliner traffic is down now to 0.03 fatal accidents per million flight hours. So it is the safest way to travel, is in an airliner today. And that improvement, and this is an Airbus chart, is a result of several things. One is the innovations that have happened at the system and the component level, but another is the improvements that have happened in the way aircraft are operated, pilots are trained, aircraft are maintained, aircraft are controlled in the skies. Those improvements are a result of this just culture that the aviation industry has embraced over the last 30 years. And by just culture, it's reflecting that if something bad happens, the focus is on why did it happen, what were the causal factors and contributing elements, and what can we do to make sure that won't happen again. Whereas a lot of other industries, when something bad happens, the focus is exclusively on culpability. Whose fault is it? Let's punish somebody. And then what happens when you focus on culpability? We see it in the United States with, for example, firearm accidents between law enforcement officers and citizens. You don't get to the root causes of what caused the accident because everybody gets into defensive mode. The aviation industry has been stellar at learning from everything that has happened. And as a result, you've had regulations grow, you've had procedures grow, and you've had rigor go into the industry. What you do see is at the top, those are the 4 different curves. All those airplanes basically look the same. These are Airbus aircraft in 4 different generations. But behind the exterior is the improvements in the design and the process. There is a curve that's inversely proportional to this, but at a steeper rate, that I didn't include here, which is the average time it takes to accomplish certification for a new aircraft type design. So the time for certification was less back in 1970, 1980, 1990 than it is today. And over the last 25 years, it's gone up substantially. So the improvements that have happened in the processes and the rigor of certification to address all these accidents that people have studied to adjust culture have fed burden back into the certification process. So we're at a point in this curve now to get through this barrier to entry, the fact that it takes so long to certify a new aircraft, is we have to come up with ways as an industry to be able to satisfy the rigor, but do it in faster time. And that's where these innovations in digital technologies, analytics, and artificial intelligence can come into play. So what are some of these, just to summarize, what are these barriers to entry? And how are these getting taller? And then we can talk about how to mitigate those, and I can share some personal experiences. Number one is just capital intensive. To launch a new aircraft program takes a lot of money. And if you look at new aircraft companies that have started, you know, the Stephen Fitzpatricks of the past that have been an entrepreneur, started a new company to produce a new type of an aircraft, most of those have failed and most of the investors have lost their money. And so now you look at the consolidation of a whole lot of companies that we had in the first 60 years of aviation to now just a handful of OEMs and in the duopoly in the large airplane, that there's no incentive to invest a whole lot of money to develop a risky new type of an aircraft. So I previously worked for Leonardo. Leonardo Helicopter Division has a backlog that's more than 4 years. So if you wanted to buy an AW169, you would order it today to get it delivered more than 4 years from now. The only reason you do that is if there's no other option. And then from Leonardo's perspective, they're selling more helicopters per quarter than they're delivering. So their book-to-bill is greater than 1, which means their backlog keeps getting bigger. So their incentive is to spend their cash to improve their capacity, improve their rate at manufacturing, drive down their manufacturing costs, not invest it in a new aircraft because they don't need to. They still have the demand. So the capital intensive element of it is a driver. The second, as I mentioned, is aviation is a heavily regulated industry. And it should be, right? I mean, this is something that we have debated periodically, such that have we hit in commercial aviation the point of diminishing returns, in that the new regulations and the recently added regulations add more of a burden than the benefit that they provide. EASA, the United Kingdom CAA, the FAA have all instilled processes in their rulemaking to make sure that they review that before they put a new rule on the book. But now if you look at it from an aggregate perspective, there are some debates ongoing, in particular in the eVTOL industry, as to whether or not the regulators have gone too far. And now it takes you, on average, 10 years for a new VTOL aircraft to be certified. 2 years and $1 billion plus. Number 3, barrier to entry. In the airplane world, is there anything else that's a low-hanging fruit or even halfway up the tree piece of fruit that we can invent and innovate to be a step-changing capability? Or has most of that already been done? So is the industry overall technologically mature, and that's why we're not seeing innovations? And if you think about big, risky technological advances, in the past, a lot of those have been driven by defense departments. Those have been driven by public impetus to produce a new capability. And the last one is the big one, is the lack of competition. If you don't have competition, like the Leonardo example, you're just not going to see the level of innovation that you would if you had a lot of competitors and startups. All right, so we're starting to see momentum. This is a curve that shows the investment over the last 15 years in electric vertical takeoff and landing. This is a combination of public and private investment that is seeing, hey, there is a demand and there is a technological opportunity to meet that demand. So this is the Stephen Fitzpatrick moment in Sao Paulo, that a lot of people are having it and the investment is kicking in. This also requires the public support, and the last bullet on here is an important one. The regulator needs to come along on the journey. People in my industry, our industry, love to talk bad about the regulator. Right? It's the one thing that everybody can sit around at the lunchroom and complain about how the regulator is making our life difficult. But you think about what the regulator does for this entire industry. And you talk to your family, you talk to your friends, you talk to your neighbors, and they're comfortable getting on an airplane at Heathrow. And the kids are smiling, everyone's happy, they're going on a holiday, they get in, they're not afraid to be defying gravity in the air in an aluminum tube. And that's because of the currency of trust that the regulations provide. The regulations are the currency of trust. You can get in an airplane and trust that you're going to get there safely because of what they do. So to be able to move the curve in new aircraft design and overcome those 4 barriers, we have to have some type of an impetus. Here's an example. Mobility in and around populated areas. The Cambridge, Oxford arc. I moved here a little over 3 years ago from Philadelphia. And the Cambridge area and the Oxford area are these hotbeds of new companies and growth opportunities for the economy. But it's really hard to get there. I was in Cambridge a few weeks ago, and I live on the Wapping Wharf in Bristol. It took me 4.5 hours to get from Cambridge to Bristol. 4.5 hours. You're looking at a map. It shouldn't take 4.5 hours, but it took 4.5 hours. Now you talk to the people that commute in this area and the economic opportunities that mobility provide, and people just can't go from one point to the other because of the inability to get from one point to the other. Then this boils down to a public requirement, the public need for the infrastructure for mobility. So where are we on infrastructure today? In this country, and in a lot of countries in urban areas, there is a very difficult paradigm to create new infrastructure for mobility. You have to go build new roads, and to do that you have to disrupt the current avenues of transportation, or you have to create new rail lines, or you need to come up with other ways, like what the city of Boston did, where they had the big dig. They said, hey, we're just going to dig underneath, and that ran, I think, $2 billion over budget and took 15 years. So if you're a public decision maker, it's a tough decision. What do? Do you widen the roads? Do you come up with a new rail line? But there's going to be resistance any way you look at it. But if you're sitting in traffic, which nobody likes to do, you look up. The birds aren't queuing up, right? There's plenty of room up there. So unlocking the third dimension is one way. So just look at some of the numbers right now. And the public decision makers are struggling with this, not only in the Cambridge, Oxford arc, but all over the world in congested areas. This is time. This is time that people lose to live their lives being stuck in traffic. So to take a taxi, to hire a taxi to get from the 67 miles from Oxford to Cambridge can take you 2.5 hours and cost you £200. Now that's costly in 2 ways, because time is valuable. That's the one precious asset that we all share. A rail line right now, it's even worse, right? 3 to 4 hours to take the train routes that we have today. Now the new lines that have been proposed could get us there, but right now there is no solution. So it's about time, right? Advanced air mobility is about time. So let's look at what it's going to take to be able to get this new capability in aviation out there. So what is the impetus? To make this a public accepted new technology, number one, it has to be affordable, right? To have mobility for the masses, we can't have a new transportation system that's just the same paradigm as business jets for the wealthy. So it has to be affordable. It has to be fast. There really has to be a strong value equation for the value of the time saved and the ability to not have to do the alternative of a big public investment in another form of infrastructure. Then the third is the passenger experience. So the public needs to want it. There needs to be a demand. It needs to be affordable. It needs to solve the problem, but it also needs to have a passenger experience that is acceptable. So here are some routes that have been mapped up in the Cambridge-Oxford arc. To be able to take that 2.5-hour, 200-pound taxi ride and turn it into a 24-minute air taxi to cover the 60 miles and do it safely, comfortably, at a price point that's competitive with the taxi, to start with. So how can that be accomplished? So if you think about it, it's a new type of capability. We've looked at what the barriers to entry are. How do you get over those barriers to entry? Well, you've got to make sure that it's fit to the market and it's fit to the safety requirements. So from the regulator's perspective, airline travel is the safest way to travel. So how about just show of hands? Who feels comfortable from a safety perspective flying in a helicopter? All right, who doesn't feel comfortable from a safety perspective flying in a helicopter? All right, now this is an aviation group, right? So if you do this at a party with everyone's partners there, it's going to be heavily weighted on the not comfortable in a helicopter. And the data does support that, right? So if you look at helicopter accidents in general, there are about 500 helicopter accidents per year across the globe. 100 of those are fatal. And that's out of 5 to 7 million flight hours. Whereas you've got 2 orders of magnitude or more, at least, in the commercial airline. And as we showed, there's 0.03 fatal accidents per million flight hours. So it's much, much lower. So the approach to overcome that is from the start, design it to airliner safety standards. Those standards are there, they're mature. If you looked at the accident rate over these past 60 years, it's really, really gotten better. And that's because of this learning and these criteria. So in an aircraft this size, that could seat 4 passengers in the back and have 2 seats in the front, but only require 1 pilot, can you get to that airliner safety standards? And the answer is yes, with today's technology, and you do it from the get-go. Being an electric aircraft, it comes down to just more EMAs, more electric motors, more silicon chips, and more high voltage cables to be able to build that into the safety standard. And if you take the safety standard, and fortunately for us being located in the UK, the CAA has adopted what EASA did 6 years ago to lay out a very detailed set of criteria for eVTOL. So we have a clear path. Now, some of these are pretty burdensome, like a 40-knot gust flow we have to design the aircraft for, and a 12G crash landing, either longitudinally or vertically. But if you design the structure from the start to meet that, if you know your requirements and you do that system engineering up front, this is a solution that can happen. Passenger experience, this is listening to the market and see what the need is. The initial need is to be able to get people to and from the airports and to use as much of the existing infrastructure that's available. We all know how difficult it is to get to airports. That is an easy mission that the eVTOLs can launch service in. But to do that, you need to have the baggage bay that can accommodate that, because if people are going on holiday, you should expect 2 bags. So we've sized the aircraft, and we're the only eVTOL aircraft that has done this, to be able to fit 2 bags per passenger. Second item is the safety aspect. If we talk to the airlines who want to be able to sell 1 ticket that can take you from here to the airport in an air taxi, and then take you from Heathrow to New York City in an airliner, and then take you from New York City to Princeton, New Jersey in an air taxi. They want to sell you 1 ticket under that airline's brand name. So they want to be able to have that safety standard that they're used to, which includes a partition between the pilot and the passengers. So again, it's the only eVTOL aircraft, the Velo, to have that partition between the cabin and the pilot. And then the payload and the range, which is driven largely by the technology available in lithium-ion battery cells today, what type of energy density and power density you can get. But similar to new types of helicopters, if you design it for growth and then have a growth strategy, a product roadmap, without having to recertify a new airframe, that's the strategy that was built into this aircraft. Because of that long, expensive, new type design certification, the aircraft's designed to be able to fit 6 seats. So here's a bird's eye view of a cutout of the aircraft. It's initially going to seat 4 because today's mass-produced lithium-ion battery cells have a certain energy density. It's about 200 kilowatts per kilo. And that energy density with the empty weight of the aircraft will allow us to fly 50-mile missions. So it's a 100-mile dry tank range, but 50-mile missions with mission reserves, and carry 4 passengers, 550 kilos of payload. So 4 passengers with 2 bags each and 1 pilot in the front. But the lithium-ion cells, if you look at what the producers are doing in their labs, we have some cells down at Avonmouth that show a 15% improvement in energy density, and the projection is those will be in full rate production in 18 to 24 months. So we project out and say, okay, in 18 to 24 months, we'll be able to take that 15% to the bank and remove energy cells from the battery packs. Now the battery packs are between 1/4 and 1/3 of the overall empty weight of the aircraft. And they're located right underneath the floor in the CG location. So by taking out the cells, because you've got more density, energy density in existing ones, gives you more payload at the same takeoff weight, same airframe, same motors, same battery packs with form, fit, and function cells replaced. Then we put a 5th seat in. Or we adapt it to a higher payload mission such as an EMS or cargo. Vertical takeoff and landing aircraft have the ability to do a number of missions. You think about our medical. Kind of a story that hits close to home. A friend and a neighbor of mine suffered a stroke while on holiday at St. John's Island in the Caribbean, just after the Christmas holiday. And the life-saving ability to get a helicopter to airlift him to Miami was the key. But they almost didn't make it. It almost took too much time to get him there. And when you go back to that model with the hospitals and the medical teams, it boils down to just how expensive it is to operate a helicopter. And when you take a helicopter into Miami, they're high-end neighborhoods right there. So the neighbors don't want helicopters coming and going a lot. So they've reduced the number of air medical helicopters that can operate out of Miami, which makes it riskier for somebody on holiday in the Caribbean because of how loud they are and just because of the economics of it, how expensive they are. So the beauty of the eVTOL in this innovation space is to drive the operating cost down because you replace these really complicated, expensive to build and maintain gearboxes and rotor hubs, rotor controls, and replace it with, and turbine engines, and replace it with electric motors and lithium-ion batteries and wires and silicon chips. So by driving down the operating cost and dramatically reducing the noise, just like the difference between driving an electric vehicle and a diesel car, is the noise is much lower, and that makes it more acceptable to operate in the communities. On average, we heard from our customers that they carry 75% load on average. So we're going to certify Velo to be able to have 4 seats and 550 kilos of payload. On average, an airline will fill 3 of those. So what we also heard from the airlines is that they saw just after COVID, and they're expecting this to come again. They found a bottleneck in having enough pilots certified to operate as an ATP, an airline transport pilot rating, because of the 1,500 hours of requirement it takes to get an ATP rating. So you have to have 1,500 flight hours. So what they're looking at is a model where they can have short-haul eVTOLs and then medium-haul hybrid VTOLs and use those to gain hours for the pilots. And being able to have a cockpit that really only needs one pilot to fly it, because it's fly-by-wire, heavily automated, simplified vehicle operation, but have room for two, the airline's like, that's terrific. Because if they have an extra seat, they put an extra pilot on board, that pilot gets hours, basically for free, and then that allows them to have pilots move up to the next level, and then to the next level to fly Part 121. And then the operator, to go from 4 seats to 6 seats when the battery cell technologies get better, 15% in 2 years at a 5th seat, another 15% 2 years after that at a 6th seat, then that allows them to increase their productivity by 50% to go from 4 to 6. From a company's perspective, and this is part of what we've been trying to show the investment community, is you make the money on selling the aircraft, but we all know in the helicopter world in particular, you really make your money on the aftermarket. Now there's a little bit of a trade-off here, because if you don't have as complicated mechanical systems, turbines, gearboxes, a lot of critical parts that have to be inspected and replaced, and fatigue critical and life limited, well then you're going to drive down your aftermarket revenue, which are the most profitable. So the aftermarket for these types of aircraft is the battery. And so that's why as a company we're focused on the battery technology. And the battery is a neat proposition, because to be able to take off and land vertically you need a lot of power in a hurry, right? Boom, you take off. But when the battery cells degrade to the point that it doesn't satisfy its power assurance, you can't quite guarantee enough power to take off in an emergency or hover in an emergency, you can still then use it for other applications, right? You could use it for a plane that doesn't need the vertical takeoff landing. You can use it for automotive. You can use it for industrial. So the plan is to take the batteries that failed power assurance, put a new one in the vertical takeoff and landing aircraft, sell that back to airplanes, recycle it, and then it can't do an airplane mission anymore. They can sell that back into automotive, or sell that back into industrial or into electric grids. So you get this ecosystem, this economic value that captures several times over. So for each eVTOL aircraft, each payload that we sell at Vertical, we're anticipating over the life of that aircraft, over its 20-year life, we're going to get 2 times the revenue on the battery replacements, largely because of this ecosystem. Then the other item that we see as a public impetus is the dual-use nature of an electric hybrid aircraft. So a 50-mile range mission with the requirement to charge takes a lot of the versatility out of various defense missions. But with a hybrid power plant, and again, think back to those 12 bags that could fit in the baggage bag. Taking that baggage bag and putting a firewall layer, making it a 2-story, and putting a gas turbine in there and 4 turbo generators, and use those generators to power the batteries when you're in cruise condition and the aircraft is cruising on its wing at a low power setting, and then when it converts back to hover mode to land, go back to electric and be quiet, is a solution that then opens up the payload range so they could fly 10 times longer, up to 1,000 miles and carry more than 2,000 pounds. So the shape of that payload range curve has a knee that's more than 500 miles and more than 2,000 pounds. And you think about the missions that you can do versus the price point compared to a helicopter in terms of total operating costs at about half of what is out there now. So I did want to make a point here just because I think this is an important discussion point for the industry. And eVTOL, and in particular the VTOL being developed here in Great Britain, has created a little bit of a debate within the VTOL world in terms of what is the appropriate safety standard. So if you think back to the slide that was presented earlier, that talked about the diminishing returns curve, has the industry gotten to a point where the regulations are so strict that the extra time and cost it imposes doesn't give you that payback for the safety benefit? Or is that the right standard that we need to continue? So this is the data that will essentially answer that for you. If you look at where we are, 0.03 fatal accidents per million flight hours. This is the airliner Part 121 standard. Safest way to travel. If you look at general aviation rotorcraft, it's 360 times worse in terms of the number of accidents. This is what leads to the 500 accidents per year, 100 which are fatal. So the difference is more than 3 orders of magnitude in the safety standard. So the ability, is this necessary to get to or not? From our opinion at Vertical Aerospace, the answer is yes, and that is what EASA and the UK CAA has established. Because for any new industry, we're talking about this during the dinner hour, is that if there is an accident, the visibility that aviation accidents get can set the entire industry back. So the safety payback is huge. The standards are out there, they're mature, they're tried and proven. The ability to get to it is a 350, 360 improvement in the accident record. And it's not just the 10 to the minus 9, the 1 in a billion, which is one of the big drivers in the redundancy, but it's also all the criteria that goes into size the structure, such as crashworthiness, gust loads, and other types of structural loading. There's also the model within the European certification that's different than the FAA. And one of my former colleagues at Leonardo used an American football metaphor. They said, okay, if you've got a certification program with the FAA and you've got the ball and you're going down the football field, they said it's hard yards all the way down the field from where you start. Because when you start doing your prototype flight testing, the authority's with you, making you show the airworthiness data after every test. So what we're doing now at the Cotswolds Airport is we're doing tests that are right at the end of our envelope expansion, and when we find something where the oscillatory load spectrum is a little higher than what we expected, and we have to go back and prove that we don't have to change the life limits in our maintenance manual relative to the fatigue spectrum that we tested it against. And then update those documents and get it signed off by our CVEs internally and then by the CAA. But what that allows us to do is do the hard work now to earn the trust and then earn the privileges so that downstream our design organization, approved design organization, can do those approvals without the CAA's involvement. On the FAA side, they said the football metaphor is it's easy yards until you get to the red zone. Now the red zone in American football is you're within 20 yards of the goal line. They say once you get to the red zone, then the defense becomes almost impenetrable. And then when you get close to the goal line starts to move on you. Because that's when the authority gets involved, technically. And they look at it and say, ooh, I'm not quite sure if that's the right spectrum. Go back and change that part or change, and then it's more impactful at the end. So the model that's been put in place with the EASA is the reason why you see a lot more type designs being certified in the helicopter world, at least in Europe, than you have with the FAA. And I'm not sure if my friend Carlos talked about that at all when he talked about the 525, but it's one of those paradigms that has been improved over the years here in Europe and in Great Britain that we at Vertical are taking advantage of. Now, the other thing just to mention on this, which is I think an interesting story, is that the FAA has released their eVTOL certification requirements in what they call performance-based format. So instead of having a thick set of requirements that have all the specific criteria, for example, to tell you exactly what types of energies you have to inject into your aircraft to show that you can withstand a worst-case lightning strike. It doesn't say that, it just says you need to be able to survive a lightning strike. And so then the applicant has to say what that criteria are. Similarly, for crashworthiness, it says the occupants shall be protected in the event of a survivable crash landing. And so it has all that nuance versus what's in the rules now and what we have with the EASA and the CAA. It tells you exactly what the crash landing criteria are, and exactly how you impose the attitudes and you crash it longitudinally and vertically, what type of factors of safety you have to put in, and what exactly that survivability means in terms of structural integrity and heavy parts in the cabin coming loose. So that gives a clear path. So the opaque power lift certification standards of the FAA is such that not only is it not published what the criteria are, but in terms of the means of compliance, the FAA said they're not even going to publish that, they're going to treat it as proprietary. So why would they not publish if somebody has an argument that says, hey, we've got a better criteria, not 12 Gs, but 8 Gs with a different attitude? It's largely from a responsibility and a culpability perspective that it would be difficult for an authority to drive down a standard relative to something that's out there now and publish it. Instead, they will push that responsibility onto the applicant. But that does create a difficulty in the harmonization across the oceans. But what we see this as a business is an opportunity, because EASA and the CAA have made it clear they've got their criteria established and it's published, that gives us the portability to other nations and say, hey, here's one that's clear and transparent, or you would adopt the one from the FAA, which is opaque. So the last thing I wanted to mention is the maturation of the technology. You need a clear path to certification. You've got to have the public impetus, but then you have to prove that the technology is mature. And we're doing that through flight testing in the Cotswolds, and we're proving the market fit of the aircraft through a comprehensive team of customers and suppliers that are providing that collective wisdom to make sure that it's not just a team of 450 people in Bristol, but we're bringing together the collective wisdom to ensure that we've got the right design and bringing in this network of operators to tell us exactly what's market fit. The Vela will spend 90% of its time in the cruise condition, and if you get a chance, please let me know when you're around the Cotswolds Airport, and we can, have you stop by and listen to it in the cruise mode. Because if you listen to it in the cruise mode, it's just a very gentle roaring type sound, is how it's been described, which is a paradigm change relative to what you have for vertical takeoff and landing aircraft today, where you have it fly over your house and you can hear it coming before you see it. For the Velo, you're going to see it and you're not going to hear it. So the flight testing has been done through a comprehensive, rigorous envelope expansion test program, and we are right now in phase 4, right at the end of the S-curve. Right, in the aviation business, when you're trying to qualify something new, you've got that progress that looks like an S. The first few tests pass, take a little while, and then you get to a steady state. You're completing and passing your tests at a given rate, and then right at the end, you're at the top of the S, where you will find the areas that you have to go repeat and make some adjustments, and we're right at that make some adjustments, redo the paperwork, tweak a few fatigue assessments and part lives based on different spectrums of oscillatory loads, get those approved, and then go repeat those last few conditions with the adjustments to the software. And then phase 5, I'm really looking forward to, because that's going to give us the ability to take our full-scale piloted flying prototypes, with 2 of them, aircraft 2, aircraft 3. Aircraft 1 was a full-scale unpiloted that we could do risky tests with. We'll take these 2 and we'll take them to different parts within the country and start evaluating operational procedures and infrastructure. And we're going to start by looking at the Cambridge-Oxford corridor. There's a vertiport in Vista where we teamed with Skyports to do some development, and we want to start to get some more real-world experience flying real-world mission sorties. But then what we also want to do is get the public to see it, hear it, touch it. Because as with anything new, you have to get that public impetus. We have to get that public acceptance. We're confident that once more people can see it, then the awareness level will go up and the momentum will continue to increase. Last thing I wanted to talk about was the batteries. So we were doing the technology development on the aircraft. The other thing is the batteries. And the batteries, the basic technology is from automotive, but has to meet the safety standard for aviation. So the safety standard in terms of what's called thermal runaway, catches on fire, is you have to take 6 of the cylindrical cells and ignite all of them on fire at the same time. You inject a short in there and light them on fire and show that the packaging of the battery pack does not propagate outside of that module for 20 minutes. So the aircraft continues to fly for 20 minutes if 6 catch on fire at the same time. And now we've already had to prove that one can't propagate to the other. So these are 6 independent failures. Now the reason 6 is because there's over 1,000 cells within an aircraft battery pack. So that probability then increases just because the number of them, but still it is a really conservative criteria to show that it contains it, vents the hot gas out the bottom of the aircraft, and allows the aircraft to fly and land safely, and the passengers all walk away. Then the other is just the crash, is to drop it from 50 feet and show that the battery does not produce any hazardous effect from that level of a crash. And that's been large focus of the effort. All right, so I'll take questions now. This was just a summary in terms of what we need to do. The call to action is that with this innovation problem that we have in commercial aviation, what we need to do is get the public impetus. We need the collective wisdom to come together. We need to create that need and that demand. We have several aspects that we see as the demand. There's the dual use side, right, to be able to support the defense. There's the urban air mobility that solve the congestion problem without more infrastructure. There's the clean skies aspect. But then there's also just the economic growth. There's the injection of new innovation into this community that's has this proud aviation heritage and this deep and wide talent pool right here in Great Britain, we have an opportunity to inject this additional energy, this additional investment, private investment with public support. But to do that, we have to capture the public awareness and the collective enthusiasm of this industry. All right, thanks. All right, questions? Oh, yes, sir.
Okay, well, a few, but I mean, you hit the nail on the head with public acceptance. You know, that's an issue within aviation generally in the UK. You know, not as it is in the US, where it's an everyday thing. And you actually mentioned Cambridge Airport, which is closing down and is becoming a housing estate. And Gloucester the sale of Gloucester's fallen through. And most airports in the UK are seen as being fair game when it comes to houses. So the locations of these things become sort of narrowed down to a very, very small proportion. I mean, you weren't vertically taken off in that show. It was a standard climb away there. And equally so, if I wanted to take 3 passengers in the PA28 into Heathrow, the simple answer would be a big no. So what makes you think that your product would be any different going to Heathrow?
So that's a great question. So to start with the first part is the public officials. There is a resistance to invest in aviation for 2 reasons. One, the general aviation infrastructure is seen as, number one, it's where the wealthy land, right? The royal family lands at our Cotswolds Airport, and Taylor Swift landed there too. And so people look at it, okay, we don't want to invest in that. And then it's also, it's for the enthusiast, right? It's for the general aviation sport. And so the public does not have a lot of sympathy for that. So we have to change that argument, right? We have to change the narrative. It's not just about the wealthy and the aviation flying enthusiasts. It's about a public need, and it's about mobility that everybody can benefit from. And then number two, it will require infrastructure development, and there will be difficulty saying, wow, we got a million things to do at Heathrow. Last thing we want to do is come up with a runway independent approach and some infrastructure to be able to take the eVTOLs in. So for that, it's an incremental. Okay, let's get it out there with some simple infrastructure. Let's get a couple of vertiports, and that's why I think the Cambridge-Oxford corridor is perfectly suited, because, as you said, we've got some general aviation already in there. We just have to revitalize and say, here's the need. It's a public benefit, mobility, and it's an economic growth benefit as well. Change the narrative. It's not just for the wealthy, it's for the public, and it's for the economic growth. And then the next step would be working with the airports to say, all right, see, we've proven it here, let's expand it to really get the benefit. So same at JFK Airport in New York City. Right now, Blade, which was just bought by our competitor Joby, operates from the 2 heliports in Manhattan to JFK, but it doesn't go to JFK. It goes to where the rental cars are at the Jamaica station. And then you have to get and carry your bags and go up the lift and get to the monorail and walk through a bunch of hallways, and then take the monorail and then walk through a bunch of hallways. So it's not ideal. The next step would be, okay, we can do that for start, then get the infrastructure at the airport. Yes?
So I was looking at your development journey and the stages that you have there. And I saw in every stage you had stability with single effector failure. Can you talk a little bit about that journey and how that's going?
Yes, so the failure matrix on this aircraft is, I don't know what a good word to say, it's daunting. So there's 30 separate control effectors. So if you count all the surfaces, and this doesn't even include the redundancy that built into the EMAs, the electromechanical actuators. There are 30 of them, also because the two main gear brakes are electrically controlled for ground steering. So the matrix of failure conditions is huge. So again, it's, hey, we have to come up with a smarter way to condense the certification, prove that the models are accurate by selecting a few key failure conditions and going to prove those in flight. So we picked the few of the key conditions. It was the tilts with the big one, the tilt and the EPUs. So the motors, the 8 motors, are a primary control effector in addition to the propulsion system. So if you look at the 8 motors and you want to roll to the left or translate to the right in a hover, you change the thrust on the left wing versus the right wing. And similarly, if you want to yaw in low speed, you change the differential tilt angle, which is similar to what 609 has, which uses differential longitudinal cyclic. So the critical failure conditions were the failures of the tilt system and the failures of the EPU. So those are the ones we tested. The surfaces, we tested those on the ground because of the redundancy that we've got 6 on the tail, and then we have 6 on the wings. It was benign, similar to what was predicted. We just did some high-speed taxi tests to prove that and said, hey, that's good. But we have to get the momentum for that on certification because it's this huge matrix we got to go prove. We want to be able to use simulation to prove it. Yes?
What sort of turnaround time are you looking at? I'm thinking about the time it takes to charge an EV these days. What sort of problems are you going to encounter?
Yeah, so we've adopted the common charging standard, CCS, for the infrastructure, but we built dual charging circuits into the battery, so we can take a high current charging CCS standard and then split that, so we're charging 4 batteries with one stream, one power line, and power charging distribution system, and then the other 4 with another, to get us to a 15-minute charging time for a typical 20-minute sortie. So on average, the sorties will be about 20 minutes, which is about 30 miles, 30 to 40 miles, based on just looking at what our customer base says. And then 15 minutes, you're exactly right. That ended up being one of the few KPIs, right? Payload, range, and how long it takes you to turn around and charge. Because what the airline said is that for them to make their margins, it's how many sorties they can do in a day. And how many you can do depends on how quickly you can charge it. And doing it faster than 15 minutes might be too fast because they still have to get the bags off, get the new bags on, get people on, get them off, do the safety briefing, get everything closed up, locked up, pre-flight checks. So 15 minutes was what we found to be a good sweet spot.
Yeah.
Yes.
Well, going on from that, surely that limits the locations that you can use because the amount of power you require from the grid is going to be very high, isn't it?
Yeah, so it is one of the infrastructure drivers, is to be able to meet it. But the key was to get that standard published. So the key was to be able to get that public support and these industry consensus committees. So it was a great opportunity for engineers to kind of put their heads together and say, okay, this isn't just one company that defines the charging system. We need everybody. And so we had some really smart people from the automotive industry come in, some people really smart in infrastructures and community power lines, and say, okay, what are the trade-offs? And it was about a 3-year effort, and it was published about a 1.5 years, 2 years ago. Yes?
You mentioned about the public trust or lack of trust in helicopters. Admission, I'm not an aeronautical engineer, I'm a friend of the RAS branch. But I worked for 20 years in the forensic medicine unit in Edinburgh, starting shortly after Lockerbie, so everyone I worked with had worked PA 103, the big MOD helicopter crash in Kintyre. I just sort of thinking socially, I don't think I ever heard anyone talking about being frightened of helicopter flight, just, sitting in pubs or whatever. Never heard anyone say it. There's a thing in Scotland called a fatal accident inquiry. And it's like you're talking about with the air inquiries, that it's not about assigning culpability, it's finding out how did this happen, can it be prevented from happening again, what should we do to stop it happening again? And that's been going for 100 odd years for anything that's an unusual way that anyone has died, basically, in Scotland. And they're really widely reported on. The tabloids report on them. Whereas, having moved down here 12 years ago, the reporting here is it's very much high-profile people who die in helicopter crashes. It's the owners of football teams, it's baseball stars, and it's really wound up in the newspapers in that way. And there's no subsequent factual reporting of this is what happened. There are no mentions on talk shows and things about, well, these are the findings of the FAI. I'm just wondering if it would be really interesting if you ever give one of these talks in Scotland to find out if there's a difference in
that is a really good point, because you're right. In airplanes, they do follow up. The media, the mass media, follows up and said, "Here's what happened. Here's what happened. The accident in Louisville with the cargo. Okay, the engine mounts broke. Here's what happened." But there was a fatal accident of a helicopter last summer in the Hudson River. 6 people were killed. A whole family was killed. It was tragic. And they still haven't published what happened yet. So I was at the show in Atlanta. I said, when's that going to publish? And the people are like, well, they're still not sure whether there was a bird strike, because they found some bird debris, but the parts were in the Hudson River for a long period of time. They pull it out. It could have been some bird debris. A bird had died and landed in the river, and they don't know whether it was. So they said they're still struggling with that, but it's not getting the attention. But the other thing to keep in mind is, you think about the helicopter industry. They are operating, in general, older helicopters. And so it's the grandfathering. So the Bell 206 that crashed in the Hudson River was certified to 1960 safety standards. So would you allow your family to get in an automobile that's to 1960 safety standards? Or airplanes, right? Because airplanes now have evolved, so they're all current, because the airlines need to. So you think about that, they're grandfathered in, and that's why some of the modifications that have come into the regulations haven't made it into what's operating for the tour operators yet.
I've owned 2 aircraft manufactured in 1966, and I'm quite happy to fly them. Along with my family.
Sorry,
Yeah, I love the Bell 206 too, to be honest with you, but I do have had a couple of close calls.
Absolutely fascinating lecture. A great combination of the financial side of this business, the detail and design, the forward-looking of how improvements in battery technology will allow take some batteries out and put more seats in and make the business case even better. The forward-looking of what to do with those batteries when they lose the 100% ability to lift vertically, and how they trickle down into aeroplanes and then eventually cars or industrial. Absolutely fascinating. And I liked your analogy to the American football of the 2 different ways of qualifying, the EASA CAA type way of doing it and the FAA. From my point of view, one of the most difficult requirements in a specification is where it says apply an appropriate factor. You know, as you made clear, we want to be told the factor so we can work to it, and not come up with something that's appropriate and hope that when we get to certification it's going to be considered appropriate by the authorities. So, but the American football analogy was excellent. So thank you very much, David. And I'd just like to invite the audience to show their appreciation in the usual way.